Good afternoon, everyone. Okay, we'd like to start. Okay, we're very happy. Welcome to the last seminar of this semester. We'll be in a semester break for the next couple of months until the next semester. Today, we're pleased to have with us Oren Shriki from Beersheba. Oren did his PhD here at the Hebrew University with Chaim. After his PhD, before he went to do his postdoc at the US, he spent 9 years teaching high school students, high school physics students, which I know actually, because he knows that he still holds connection with many of his students. Some of his ex-students actually working in his lab now in Beersheba. Now he heads the computational psychiatry and neurotechnology lab at Ben-Gurion University. In his lab, they combine mathematical analysis of brain activity with machine and deep learning algorithms to develop diagnostic tools for neurological and psychiatric disease. Some of his current research focuses on dynamics of the epileptic brain and the neural basis of conscious experience. Beyond his research, he's done a few other things in the community. One of the most interesting one is the foundation of Brainstorm. So Brainstorm is a student-led community combining neuroscience and technology. We have some of the community here in Jerusalem. Someone started this community in Beersheba. And also in 2021, he founded NeuroHelp, which is a startup dedicated to creating wearable systems for detecting and predicting epileptic seizures. And today we're going to hear about cognitive and clinical perspective on the framework of clinical brain dynamics. Oren, thank you.
Thank you very much, Jonathan, for the invitation, and it's great to be here. I see all the many familiar faces. just start. So just a few words about my lab so people know. The current major research topics are epilepsy, as was mentioned, seizure dynamics, detecting seizures, computational models related. Another is brain-computer interfaces, and it's a bit wide, not just controlling by thought external devices, also monitoring passive, like cognitive workload. We have a few cool projects with EEG and virtual reality combined in the context of flow, in the context of loss of ego, brain synchronization, some cool things. I will not discuss it today. And then I allowed myself not to wait until the age of 72, like Hagai, to start talking about consciousness or whatever. But I'll share some ideas with you later on. It's mainly for brainstorming and to get your feedback. And these are the main themes of the lab, this idea of critical brain dynamics, lots of EEG data analysis with all kinds of mathematical features, machine deep learning, and neurotechnology, wearable systems, these kind of things. So I want to tell you a story. It starts actually around 25 years ago when I was still a PhD student here with Chaim Polinsky, with some modeling work, which I'll briefly tell you about. And then it unfolds, and I'll tell you more stories about some data analysis with computational modeling, but eventually, as I promised, I will say a few words about consciousness. So somehow it will lead to these ideas of conscious perception, and this is what I want to get to eventually, towards the end of the talk. So a few words about the framework of critical brain dynamics. It's an idea that really started around 25 years ago. In 2003, there was an influential paper about critical brain dynamics, but in recent years, it grew substantially. There are lots of papers. And there's a community that essentially investigates the hypothesis that the brain, more specifically the cortex, operates not far from a critical transition between two different types of dynamics. And they could be different. I mean, there are different types of transitions, and the word criticality is not just one entity. So it's subtle. I will not get into all of these. And so the mathematical framework of critical dynamics, studying these phase transitions in physics, bifurcation in dynamical systems, it lends itself to describe these ideas of critical dynamics in the brain. And mostly when we talk about it, we relate to recurrent dynamics and the balance between feed-forward and recurrent dynamics. So if we don't have recurrent dynamics, we have networks that are dominated by feed-forward connections. They don't show any interesting dynamics from the point of view of criticality. Only when we add recurrent dynamics, we can get something like some instabilities. We can get hallucinations, we can get seizures, we can get chaotic behavior. So this is the main axis. Here it's not mathematically well defined. In specific context, it could be increasing both excitation and inhibition, just excitation, but increasing the dominance of recurrent dynamics can lead us to these states that can manifest in pattern formation, hallucination, or synchronize activity or other types. And we believe that the brain is not exactly critical, but slightly subcritical, slightly dominated by feed-forward most of the time. It's kind of related to these ideas, if you know, in the context of consciousness, of controlled hallucination. We use the recurrent dynamics, we use it to predict things, we use it to have prior expectations, but we still want to be connected to reality with feed-forward connections. And just to be on the same page, when we talk about critical phenomena, phase transitions, we refer to these famous transitions like water can transition between solid and liquid, or liquid and gas. There are systems that can transition between magnetic and non-magnetic phases, and they have some common interesting things. Typically, near a transition point, there is a transformation from decaying exponential activity on one side to blowing up exponential activity on the other side, but in the middle, you get these power laws. You get those scale-free, long-tail relationships. I'm not getting between what and what. We can see later, but there are power laws which reflect that the system is fractal. It has no intrinsic scales, both in time and in space. And not only that, if you look at the exponents of these power laws, like some function of s is s to the power of alpha, and alpha is the exponent, you will see there are some typical numbers, characteristic numbers that we see all over the place in different systems that They have totally different microscopic properties, but they exhibit the same critical exponents. So there's some universality, and this is what's cool about phase transition. So if we have them in the brain, it means that we can say things without resorting to microscopic details of neurons and synapses. So we started the journey when I did my PhD with Chaim around the question of what is the role of recurrent connections in sensory processing. Anatomy, physiology showed us that it's everywhere. It's not just feed-forward. And we wanted to examine recurrent connections in the context of sensory processing. And the approach was, let's start with unsupervised learning in the context of early sensory processing, early visual processing, auditory processing, and we chose an entropy maximization approach. Of course, I had lots of arguments with Chaim until we converged on something. We tried also multiple approaches. But the idea was that if we want to optimize sensory discrimination, like J and D in the cognitive context, just noticeable difference, that's a good approach. And the bottom line, the gist of it, which I'm going to tell you in more details now, is that those networks, we found that they evolved to operate near a critical transition, on the border of hallucinations. Now the story in more detail. And so I chose some kind of icons to accompany the story. Network model, there will be some other icons later on, consciousness at the end. So we started with this simple model, just two layers, an input layer that represents some sensory input, like on the retina, and feed-forward transformation to some area downstream with recurrent connectivity. And these are the dynamics, just standard first-order differential equation, feed-forward connectivity or recurrent connectivity. So each neuron receives input both from the feed-forward neurons and recurrent, sigmoidal function. And as the network, for this model, we had some simplified assumptions that the input changes relatively slowly or effectively fixed. So the recurrent dynamics has time to evolve with respect to the input. And that the network reaches a steady state. This allowed us to derive some things analytically. And we denote the steady state pattern of the output layer as the output of the network. Of course, this is not an output of the brain. This output is like activity in V1, for example. And just a couple of slides of equations. So the entropy, we chose the entropy of the output. This quantifies how much the representation is rich, how much it represents differences in the input. This is a deterministic network. So the entropy can arise only from the variability in the input and the sensitivity of these neurons to the variability in the input. And you can do some mathematical gymnastics, change the variables, express the output entropy in terms of the input entropy, or the input variable, and you get that what's important is the log of a determinant of a matrix, which is effectively the sensitivity matrix. How much each output neuron is sensitive to each input neuron. We call it the Jacobian matrix or susceptibility matrix. Something happened. It's on my computer, sorry. So the entropy can be expressed in terms of the sensitivity. The higher the sensitivity, the higher the entropy of the network, the better the network discriminates among similar inputs. Visually, we can illustrate it by imagining that this is the input space, this is a small region in the input space, so nearby points in this space represent similar inputs, and we map it to some output space and we want to expand. We want different inputs to map to different outputs. And the factor of this expansion is actually represented by this determinant. So this is what we want to do. And it turns out you can do some calculations and you will find that this susceptibility, the sensitivity matrix, is maximal close to a transition. It's as if you want to amplify in some like microphone or a guitar, you turn on the amplifier, at some point you get feedback, so you turn slightly below that point. This is where the network wanted to operate. So to summarize these ideas, because I don't want to dwell on them too much, it's published. We wanted to optimize sensory discrimination. We chose the concept of entropy. This is the main premise. That's what we can argue about, but the rest is essentially, it follows. So maximizing the entropy amounts to maximizing the susceptibility, that's how we call it in physics, sensitivity to external inputs. And when you do that, in physics, we know that near transitions, like in magnetic systems, the susceptibility diverges. At the critical temperature, it diverges. If the temperature is too high, the system is not very sensitive to external magnetic fields. If the temperature is too low, the interactions, the effective interactions are very strong relative to the internal fluctuations of the elements. The system is also insensitive. It's too stiff. Near the transition, it's maximally sensitive.
Oren, question aloud?
Yeah, sure.
Maximum entropy is completely random, something I don't understand.
I understand. It's a confusing point, so it's a valid question. From the if you look, imagine that I allow you access to look at activity of cortical neurons, okay? And so maximal entropy will be really that you will see that every time, I tell you now I presented the system, a new sample, a new input sample. Like you have, say, a monkey, I present stimuli, and you can see only the patterns of activity. And I'm telling you, I change the stimuli, I change the stimulus each time. If you see that the neurons, their activity is always the same, it means that the networks does not represent this information. Or if I see that a few neurons are highly correlated, they're doing the same all the time, again, it's some redundancy. High entropy means that every neuron spans its dynamic range. So for different stimuli, it will respond differently. And the different neurons will be uncorrelated to some extent. And these are also competing things. But from the point of view of the network, if you look at the network, you will see high entropy. You will see that if I expose the network to interesting world of stimuli, the network will produce entropy. But this entropy is coming only from the external world. I can maximize the entropy if I inject some random noise. That would be trivial. But this is not what's going on here. It's a deterministic network. So in a deterministic network, maximizing the entropy makes sense. It's a good code. As we all learned in the courses of Tali Tishby, the best code is actually like white noise. If you transform something to white noise, that's the best. It's hard to, we don't want to do cryptography in the context of the brain, but optimal code is actually code with high entropy. So the point is that in physical systems, near criticality, the susceptibility is maximal or diverges. And here it's the other way around, that the network wants to optimize sensitivity, so it chooses to operate near criticality. That's the insight. And I'll demonstrate it in just two contexts briefly. One is in the context of visual processing. So we take the network. We can learn the fit-forward connections. They will be Gabor filters. But for studying it systematically, we can just set them manually to be Gabor filters with different orientation, same spatial frequency, same location in the visual field. Now we expose the network to natural stimuli, just images, black and white, gray levels, and we learn the recount connectivity. So different neurons are responsible for different orientations, it's just a simple orientation tuning. How will the recurrent connections evolve? So they evolve to be like a Mexican head profile. This is the matrix, and this is just one row of the matrix, so it's naturally evolved to be a Mexican. Just from natural images, you don't put it by hand. So it's like the ring model, but it emerges naturally. People who know the ring model, this idea. I will not get into these wiggles, they're related to the Gabor filters and they are not general. But now, the interesting thing is what happens if we take this matrix, that this is what was optimal from the point of view of the simulation, and we scale it. We just multiply the matrix by a scalar. So if it's 0, no recurrent connections, 1, what the simulation shows, I multiply by 1, and higher than 1, let's see what's happening. So let's focus on this area. Here we use a simple measure related to the population vector, a concept that is taught here in these courses. And it's essentially what we do is we stimulate the network with some random input which is uniform, and we examine the output of the network. And we have a measure that quantifies how much it's different from a uniform response. So if there's a hill of activity around a certain orientation, we will see it. And this is what we see here is that near the point where the network chose to operate, we see a transition from uniform responses to uniform inputs into hallucinations, essentially. So on this side, the network has this set of attractors, the ring attractor, around different orientations. And even if we show it uniform input, the profile of activity in the network sharpens around a certain orientation, and you get this transition. So the network chose to operate close to this transition into the attractor regime. If you look at the dynamics close to this area, you can look at the recurrent network, how long it takes it to converge. We just let the network evolve until the activity is too similar to the previous time step. And we see a signature of what's called critical slowing down, a phenomenon which you can see in many dynamical systems that experience phase transition or bifurcation. Near the bifurcation, near the transition, they show slow dynamics. It's a collective emergent property of the network. You see very slow timescales. Here the network transitions into the attractor regime, so it remains slow. But you can see that the transitions happens at 1. We also applied it in the context of tinnitus, this ringing in the ears. So we exposed the network to some artificial auditory stimuli. The inputs represent different frequencies. We have mapping to some frequencies in the output. And again, this is some higher level area, which we assume can be related to the DCM, but it's not exactly. It's not the dorsal cochlear nucleus, but it's not one-to-one mapping. And we can let the network evolve. We first show it some stimuli. We let the feed-forward and recurrent connectivity evolve, both of them. I'm not getting into the details. There's the same objective function as before with some regularization. And then we attenuate the higher frequencies or any range of frequencies. We can do it, it doesn't really matter. We attenuate the inputs in a certain range of frequencies, and we see what's going on. So let me walk you through this figure. The top row is just 3 different stimuli, like 2 tones, 3, 4 tones, and silence. Here you see the response of the network prior to the induction of tinnitus. So these are, again, neurons that represent different frequencies, and you can see a reasonable response around some spontaneous activity. So just the network has spontaneous activity close to 0.5. Then here, again, reasonable response and spontaneous activity in response to silence. Now we attenuate the higher frequency range, just the upper half. So now the network receives very weak inputs in the upper half of the frequencies. And what happens is that these neurons, they are deprived of input, and they want to have entropy. They want to show that they are active, that they're interesting, that they're to some extent uncorrelated, but they have to increase the recurrent interactions among them. So it's built in the algorithm. If they want to maximize the entropy, they want to increase the effective dynamic range. And what happens is that essentially they switch into a mode of hallucination. They reach a critical point, they cross it to the other side, and then you see this hallucination of a tone. And there are many more details in the paper, which I'll not get into. So this model, in a moment I'll summarize the take-home messages, but there are a few papers all in close computational biology. There's a cool story about synesthesia, which I actually talked about a while ago here. And here are the take-home messages. Entropy maximization leads to near criticality. Input attenuation pushes towards near critical dynamics. We discussed critical slowing down, which could be a potential probe for networks near criticality. And then this leads me to the question, can we observe this? Can we see critical slowing down in experimental data? Slowing down is something which is relative, so you want to have some baseline and then see something that slows down compared to this baseline. So a few years ago, I heard a talk by Rafi Malach, a good friend, and he presented this work from his group where they had people living with epilepsy before surgery with electrode arrays, echo on the cortex. They presented them with a sequence of stimuli which were either celebrities or famous places. And then the subjects asked to record for 2.5 minutes. They were asked to record only faces or only places. And there were face selective electrodes and place selective electrodes. And they analyzed all this data, and they wanted to see what happens in the brain. There are many findings in these papers, and here's just one of them. If you look at the spectrum of the ECOG signal, just a word of cautious, it's you take the ECOG signal, it's not the LFP directly, you take the gamma band, the envelope in the gamma band, that's considered to be most correlated with firing rate, and it's the frequency, the spectrum of the broadband gamma. So you see very slow frequencies here because it's an envelope. What you see is that during resting state we have the blue spectrum, and during recall we have the red one. So beyond a certain frequency there is no difference. The major difference is that we have an increase in the amplitude of slow frequencies during recall. So I told Rafi maybe it could be related to critical slowing down. Let's see if we can model. And together with Dovi Elin and Noam Siegel from my lab, we constructed a simple recurrent network model. Again, same kind of differential equations like before. Random connectivity, just sparse connectivity, random connectivity, some Gaussian. So it's not a very interesting model computationally. It doesn't do any computation or learning. We can present, what we do is we stimulate the neurons with some white noise. It's a rate model, and then we get the activity of the network. We sum a fraction of the neurons, we sum their activity, and we get a signal which corresponds to the ECOG signal. And there was another paper, the paper by Chaduri, that presented this model, and they showed that you can fit the 1/f spectrum that is typically seen in ECOG data. And we can tune this model to be at different proximities to criticality. It's very easy in this model because of the random connectivities. There are some results from the spectra of random matrices, and you know the eigenvalues or how they are distributed, and you can easily control the proximity to criticality in this network. And what we were able to show is that indeed these are the real data, these are time courses. Again, when you so if you look at a phase selective electrode, this is what happens when you recall places. It's low activity, higher activity when you recall phases. And in terms of the spectrum, you see this critical slowing down. That was my interpretation, my suggestion. And in the model, we can easily replicate it. So the blue and red curves are the experimental data, and then you can see fits from the model, just from many realizations of the model, different realizations of the connectivity and the random noise in the input. The thing is that the only difference is that we tune the network from around 0.29495 to just 1% above. That's it. So the best fit of the model to the data is around 0.947, and then a small increase in the proximity to criticality, we get this kind of slowing down, which we see in the data. So it's a hypothesis, but here's what we essentially propose. That's the summary of the second part of this talk out of 5. So we suggest that spontaneous ultra-slow fluctuations that you see in the cortex, the fact that you see this 0.1 hertz fluctuations in the cortex all the time, that's already a signature of criticality. That's what we proposed. Because it's not easy to explain a cycle of 10 seconds in the data from just intrinsic processes. I remember already we had a discussion on this many years ago when you were still in Hadassah. So the collective properties of the network can give rise to these slow oscillations, but not only that. If we push the network further to criticality, we can cause it to generate patterns of activity that are stored in it. It always generates, but as we get closer to criticality, the network approaches these hallucinations. And for some reason, again, I don't know how to explain this exactly, but it seems that we now have conscious access to these patterns. Previously, maybe they happened, but we are not aware of them. And now, as we push the network towards criticality, we gain conscious access, and we can report these patterns. Yeah, I remember Obama or Clinton. And we believe that it's a simple mechanism. It's a simple idea. Maybe cortical networks, when you want to recall information from a specific category, you take these specific networks in your brain and you push them towards criticality slightly, and now you can recall from a specific category or improvise in a specific music style, jazz of some kind, or dancing, whatever. Yes?
Can training change something and shift the levels, or that's built in because of the physiology of the system?
Training?
Training, I train someone to get a higher input, other frequency.
I think training can do many things. It can affect, for example, the proximity to criticality. Maybe you can train someone to do, say, neurofeedback using EEG that will teach you how to get your brain or parts of your brain closer to criticality, and you will be more creative. I believe it's related to states of flow and associativity. Again, it's easy to throw these concepts. It needs to be tested. But I believe that, yeah, training can do something. I would also like to say that the external noise is also important. We can also increase the external noise. If the network is already close to criticality, increasing the external white noise will also have an effect of generating outputs. Yeah.
So related to that point, first that the critical point in those networks depend on the noise. If you increase the noise, the criticality shifts.
Yes. This is something that I need to discuss with you. Yeah. I mean, we set it only through the recurrent connections, just using the eigenvalue spectrum of those matrices. So when we set it to a certain proximity to criticality, we ignore the noise. We just need a minimal number of neurons,
So noise usually shifts, pushes it away a little bit, transition.
Yeah, and we see it. We see it in the
And the second thing,
simulations,
noise also destroys critical slowing down. So there's more noise you have, the exponent of the...
So in the paper, which is for 5 months now, being under review, the revision, in a certain journal, okay, I won't say the name, but in the paper we have a two-dimensional image where we explore the proximity to criticality and the level of white noise and the behavior. So you have like a phase diagram with these two parameters.
It's all there's an analytical solution.
Okay, so I'll talk with you. That's great. That's why I'm here. And so what we've seen is that proximity to criticality can change in time. Maybe our brain changes the proximity to shift into a generative mode. Can it also change in space? So that's what the icon for time, now an icon for space. And this is a recent work really from the last few months. And I'd like to share it with you. And now we switch from ECOG to fMRI data. So if you want to look at critical slowing down in fMRI, one measure that seems to be useful is something that has been used widely in the fMRI community in recent years, and it's called FALF. I knew something was going to happen. No, but my computer is still okay. Okay. So the FALF is the fractional amplitude of low frequency fluctuations. Essentially, you take the spectrum, you see very low frequencies here, and you take the integral out of the spectrum, it's very low frequency, 0.01 to 0.08, and you divide it by the total integral. That's it. So you get a dimensionless quantity, and you can take a region of interest in the brain. You have multiple, like a few hundred voxels. You can calculate the spectrum for each voxel, the FALF for each voxel, average across voxels in a certain region, and you get the FALF of that region. If you look at a region with low FALF, and you look at the time courses of different voxels, you get this kind of activity. If you look at a region with high FALF, namely slower activity, you will see slower activity, but also more correlations. You can see the time courses going up and down together. We can easily replicate it in the model. So we just tune the model closer to criticality. And we get critical slowing down. We see this slowing down of the time courses, and we see more correlations. So now we can try to interpret the data from the fMRI using this model. So if you look at this model, we can also calculate the FALF of the model as a function of the G. G is the proximity to criticality. And if you look at these numbers, you see relatively high numbers, close to criticality from 0.97 to 0.99, for example. These are just different simulations, different realizations of this random network. As we approach criticality, the FALF goes up like a power law. I kind of guessed that. It was intuitive because many critical systems show power laws near criticality, and it's related to long-range network correlation, so we could have guessed that it looks something like that, like some factor over 1 minus g, the deviation from criticality to some power. And we can estimate that. It looks nice, straight line in log-log. So now, what we can do, yeah?
So actually, previous paper showed that it's a power law above the transition, but it's exponential below the transition.
No, what G is always smaller than 1. So 1 minus G is always positive. What I'm trying to say, I'm looking only below the transition for G values smaller than 1. And as you approach criticality is somewhere here, the asymptote, like the 1, the FALF increases as a power law. I have a series of graphs that I can show on the way, but...
So we talk about the transition to chaos?
No, it's a transition to some kind of saturation, to some activity. It's not, I think in these are random networks. It's an interesting thing. Yeah, I need to, I'm not sure what is the transition, but what we see in the simulation is just as you increase the G beyond 1, the neurons just saturate.
G is a variance of that?
That's another good point. So, the network is sparse, so most of the connections are 0. The non-zero connections, we take a number from Gaussian distribution with certain mean and variance. So G is actually related to the mean. The mean is positive, so the network is slightly excitatory, but there is some variance. And you can do it also with the variance. Yes, I know that. Here, the model that we took, we control it through the mean. And essentially, the proximity to criticality is determined by 3 numbers. The gain of each neuron, the neurons are random, so they have some linear gain, the gain, the sparseness level, and the mean of the Gaussian distribution. So the product determines how close you are to criticality, and this is the number that we set, essentially.
Eventually you will have, you will end up with 2 parameters. When you do the mean field or whatever happens in each neuron, you just end up with the central limit theory, so it's about the mean and the variance. You just have a Bernoulli Gaussian distribution.
Okay. So I'll ask you later. But in the simulation, we tune the proximity, as I mentioned. Again, we followed this paper of Gurion et al. It's a simple rate model, but and this input could be really helpful for us. What we do is we take these are just fMRI maps of the FALF across the brain. So it's data from the Human Connectome project, 40 subjects, 7 Tesla, 5 minutes resting state, 180 ROIs per hemisphere. And we can translate it now to the G values. Because what we find is that if you look at the FALF values, they're all, in all areas, they are between 0.3 and 0.6. They're uniformly distributed across the cortex. We need to use this parallel relation. These are just details, but so this is a proposed map. Yeah, I'm just proposing this, showing it first. Okay. I saw it just a couple of weeks ago in Eilat, first time. We propose that this would be the map of proximity to criticality of different areas in the brain, different regions. And we see that 0.99 is actually mostly areas in the default mode network. They are the easiest to tip beyond the tipping point, to get into hallucinations, or whatever, loss of ego. Another interesting point, the take-home message that I want to convey, is what happens if we look at a certain hierarchy, like the auditory hierarchy from A1 all the way to areas that belong to the default mode network. So if you look at the sequence of areas, and we know that they process, for example, speech in different time scales, from syllables to words to sentences, paragraphs, narratives. Interestingly enough, and it is well known, if you look at the intrinsic dynamics during resting state of these areas, you can see that they have slower and slower timescales, intrinsic timescales that go up along the hierarchy. And we can translate it again to proximity to criticality. And what we propose is that proximity to criticality increases along hierarchies. You have to test it in other hierarchies, but that's the idea, that as you go to higher level areas, you need to integrate across larger timescales and across larger spatial scales, because you see hubs, like in the default mode network. And so it makes sense for the network to operate closer to criticality, where you get, just like that, for free, slower timescales and larger spatial integration scales. Regarding correlations, in the model, we can plot the distribution of pairwise correlations, and as we approach criticality, say we tune from 0.8 to 0.9 and higher, the correlations move to the right. The width of the distribution of the correlations also depends on sparseness. So we are investigating that. I will not get into all the details, but if we analyze the data, we see that now the hierarchy goes from A1 here at the bottom to default mode network at the top. The FALF goes up, as I showed you, and also the correlations, they kind of move to the right. The distribution also becomes wider, which is related to the sparseness of the network, and we're trying to figure out the most elegant way to describe this. Let's see how are we doing this time. Okay. So far, so good. Summarizing this part. So I suggest that proximity to criticality not only changes in time, but also in space. There is a spatial distribution, and it can explain the slow intrinsic timescales that we see in different brain areas, and the distribution of pairwise correlations, or functional connectivity density. I propose that it increases along hierarchies, and that the default mode network areas are at the top, which is kind of interesting. And so if we have this distribution of criticality, of course, you can also ask how is critical dynamics related to the propagation of activity in the cortex. And historically, this was studied relatively early, in early 2000s, under the name of neuronal avalanches. So I don't want to get too much into avalanches. This is the icon that just chose for this, or ChatGPT chose more correctly. But there is a major line of research in the critical brain dynamics community, which looks at the transition between activity, neural activity that terminates prematurely to neural activity that explodes. And here we look at the important parameter is called the neural gain, or the branching parameter. So we use a mathematical theory which is called branching processes and critical branching processes. And the idea is that you have some nodes of activity which are active at a given time point, they activate other nodes, and then other nodes downstream in a stochastic manner. If the branching parameter is smaller than 1, it means that on average, some neurons that are active now would activate fewer neurons in the next time step, and then fewer neurons and activity will die out. If the branching parameter is larger than 1, activity will blow up exponentially. It's this, we all know it. I mean, people are studying it for 25 years now in the context of avalanches, but we called it the spreading coefficient of the COVID during the corona time. It's the same idea, just a ratio of the number of events in 2 consecutive time steps. And somewhere in between, we have critical dynamics, and we have sequences of activations that can last for a long time or be short. There is a certain distribution because it's stochastic. And already in the 19th century, it was calculated and shown that if you took these branching processes, here criticality, the important term in the distribution is a power law. So the sizes of these avalanches or cascades of activity are distributed like a power law with a specific exponent of -1.5. And this is very general. Yeah, it's not related to neurons, to anything. And actually, it's related to chain reactions. So this kind of math is used a lot in the context of atomic bombs. And in 2003, it was shown that you can see the signature of these avalanches in cortical cultures, organotypic cultures, pieces of cortex from rats. I will not get today into the details of the analysis, but there is a recorded talk of me here at the ELSC from many years ago on YouTube. And so this is the size of the avalanches, this is the probability. So that's the histogram, and you see that it's a power law with some cutoff. So it depends on the size of the electrode array. And there are many subtleties and details which I'm not getting into, but I was interested in seeing that in human data. So this was on the millimeter scale, but if it's really scale-free, we can see it on the large human brain scale. And indeed, we can repeat the same kind of analysis on MEG data and EEG data, and we see these avalanches. What I need to mention is that the analysis, the way we divide the data into avalanches, we discretize the data and then we look at these avalanches, it depends on a certain timescale parameter. We do some kind of clustering analysis which is related to a timescale parameter, and the timescale can affect the branching parameter and it can affect the exponent. If we repeat the analysis at multiple timescales, because this is what you do when you don't know how to choose a specific timescale, and we plot here the branching parameter and here the exponent. So each time we repeat the analysis, it's the same data. These are data from 16 subjects, EEG data. As we increase the timescale from 2 milliseconds, because the data is at 500 Hertz sampling rate, to longer timescale, we change both the branching parameter and the exponent, but we see that at some timescale, around 4 milliseconds, it is very close to a branching parameter of 1, namely near criticality, and an exponent of negative 1.5, as predicted from the theory. This is EEG data, MEG data. But what we, in my lab, we are also looking at the whole curve, this whole curve, and we call it multi-scale criticality. Like we characterize the slope and offset of this curve, and it gives us additional measures to look at the neural dynamics. So I just want to show you some data. These are data during sleep deprivation. So 36 hours of sleep deprivation, 8 hours recovery sleep. And this is the gain metric, the branching parameter. And we see that it has some circadian envelope, but it grows, which is kind of what we expect. We know that sleep deprivation leads to hallucinations, to seizures. And then it goes down, even overshoots. In recent years, we have many experiments in squadrons of the Israeli Air Force. They have to, the pilots and UAV operators, they have to be sleep deprived for 36 hours. At some point in the training, we got the same data. We see this overshoot, typically after recovery sleep, which is kind of interesting. And it's also related to reaction time. So here it's in the data from the lab of Tanoni, but we see the same kind of things in the data from Israeli aircrew. And we see that after recovery sleep, reaction time goes down even more than it was in the morning of the previous day, or 36 hours, 44 hours before. And we see that the branching parameter goes to relatively low values. So as if the brain has some homeostatic mechanisms that get you back down to a normal excitation-inhibition balance and even more to the inhibitory regime. In the interest of time, I will skip the slides on epilepsy, but the take-home message is that, and I'm not showing everything, we have markers based on criticality that show differences in many contexts: schizophrenia, mild cognitive impairment, MCI, which is a precursor of Alzheimer's, and many others. It's sensitive, not necessarily specific, but we see that metrics of criticality are very interesting in the context of a wide range of neurological disorders, which are naturally related to balance of excitation and inhibition. But I had to just briefly tell you about avalanches. So neural activity can be described by these critical branching processes to some extent, nicely fits the data. And we see that avalanches are sensitive to a wide range of neurological disorders and sleep deprivation and more, epilepsy. and so at this point, I think I can get to the last part of my talk. And of course, the question at this point, after everything I showed you, is how is criticality related to life, the universe, and everything? Or can critical dynamics tell us something new or interesting in the context of the neural basis of conscious experience. So first, at the scientific level, we can take, these are again EEG data, 256 electrodes, high density from a lab in Paris. And we see that if we look at vegetative state, minimally conscious emerging from minimal consciousness, they are subcritical, like 0.7 compared to control at around 1. And if we look at our more sophisticated metrics, which will not get into details, multi-scale criticality, they can statistically discriminate between the different states of consciousness and disorders of consciousness. There are more works on that, and there are more papers published by other groups about using metrics of criticality from the world of avalanches, from the world of chaos, in the context of disorders of consciousness and anesthesia and other contexts, psychedelics, shamanic states, epilepsy, delirium. So there is a growing evidence about the relationship of metrics of criticality to deviations from criticality and loss of consciousness and other things. So all these ideas led me to propose a framework that I think is interesting from the point of view of theories of consciousness, which I call the concrete framework, short for consciousness and criticality. So there are some arguments from the theoretical standpoint. We see that near critical networks, they have properties which are desired from the point of view of theories of consciousness. Near criticality, networks show higher entropy and complexity, rich representations. They have susceptibility to external inputs. I can also show mathematically, it's not very complicated, that the network is also sensitive to its own activity. This is related, for example, to one of the ideas of Giulio Tononi that self-cause-effect power is an important property of conscious systems, that you have to affect yourself. So networks, near criticality also have this internal susceptibility. And from the experimental point of view, we see that deviations from criticality leads to loss of consciousness. We see it in disorders of consciousness, which typically lead to subcritical dynamics, but not always. Anesthetics, again, can lead to sub or supercritical dynamics. Epileptic seizures, which are typically supercritical. And psychedelics, they are thought to push the brain towards criticality and even beyond it to hallucinations. But people who take psychedelics, as you approach criticality, you're expected to have a richer sensory experience, be more sensitive to different inputs, have a richer experience, and this is indeed what people report. And then if you take larger dose, you would transition into the hallucinatory phase. So all these ideas really led to try to propose a scheme. And what I'm showing you now, again, just so what we're basically saying is we're not trying to figure out the hard problem of consciousness. But if a complex dynamical system has the potential to experience subjective, to have subjective conscious experience, and it can exhibit a critical phase transition, we propose that it will experience a heightened level of consciousness as it approaches a critical point, and the other way around, deviations from criticality would lead to loss of consciousness or unconscious states. This is an illustration in which we summarize it, and I think in terms of time, I'm very close to the end. So this axis would correspond to recurrent connectivity. So again, I'm not committing too much, but this axis, the way I imagine it is a scaling of both excitation and inhibition. That's how I picture it. And if you go here to be supercritical, you get into the pattern formation, hallucinatory regime, attractor dynamics. But again, under certain conditions, and David Hadzel is the expert on that, it could also be epileptic seizures, depending on details of the recurrent connectivity and what you change. So there's a supercritical regime, there's a subcritical regime. And this is illustrated that this is the feed-forward. It stays the same in all these images, but recurrent connections increase as you go to the right. Yeah, and again, I want to say that it could be more intricate than that. Right? It could be that feed-forward connectivity decreases, like you have sensory deprivation, but then other mechanisms compensate and recurrent connectivity increases to compensate for the decreased input, and then you cross into the supercritical regime. So just a few points. Indeed, as you approach criticality, you are expected to experience higher susceptibility, which means hypersensitivity to external inputs. You often see that in autism. And critical slowing down. And indeed, under conditions of psychedelics and even flow states, people experience time differently. What we propose is that intrinsic dynamical processes in our brain that are used by us to estimate time, they become slower and slower. And then we think that time passed quickly. Because the same process now gets very few times into the same time interval. So we think that time passed quickly, and this is what people report under conditions of peak performance, flow, this kind of thing. So it's a big story here. We won't have time to get into all the details. I learned from Hagai the distinction between dissociative and hypnotic anesthesia. So we believe that propofol and other GABAergic anesthetics, sevoflor and others, they induce hypnotic anesthesia and get you to be subcritical. Whereas ketamine and maybe nitric oxide get you to the supercritical regime. And it also means that if you're in a DOC, disorder of consciousness, and you're supercritical, we can perhaps push you to consciousness using anesthetics. And if you're on this side, we may use psychedelics and brain stimulation. So it's an idea. It's a simplistic, one-dimensional picture, but I think it can be used for stimulation and discussion. There are many implications. We will not have time now to get into all of them. And I mentioned already some of them. I think, much to say, but I think I'll skip that now and take questions. Thank you very much. Yeah, and skip a bit. So the journey started with Chaim many years ago, and Dovi analyzed the ECOG data and the fMRI data, which we got from Erez, and lots of work with Rafi. Aviv did the tinnitus work, and Iqbal is working with me on the concrete theory. Yeah. Questions if we have time?
We discussed it, but it still bothers me. Critical slowing near the critical point. I would assume that if we try to achieve to be near the critical point, this is where we'd like to be the faster, speaking from the point of the motor dynamics.
No. So what happens is that this is the reason why the brain doesn't, or one of the reasons why the brain doesn't want really to be critical. It wants to be subcritical. If you get towards criticality, you pay several prices. First, you become slower, which means, it has advantages, like for working memory, for integration across timescales, it's good. But if you need to respond to something fast moving towards you, you don't want that. So it would slow your reaction time. There's always a trade-off of you can compute better, but it will take you more time. So critical slowing down is one of the reasons. You don't want to approach criticality too much. There's also metabolic cost. And there's also the risk. You want safety margins. You don't want that some processes will easily transition you to the other side. So there are reasons why the brain, like you say, multi-objective function, you want criticality, it's good, but there are reasons to stay away. Josh.
Purely by analogy, so when you think about, when you know about sleep, you go to this REM and you sleep. Mm-hmm. And then if you don't have enough REM sleep, then you catch up on it. Is there some price you pay for spending a lot of time in criticality that requires more?
I think it's mainly metabolic, but now it's known. So sleep pressure is mostly measured using the amplitude of slow frequencies. And it may be related to critical slowing down. So, and it is shown that during non-REM stages, the amplitude of slow frequencies goes down. So I believe that non-REM stages kind of push you away from getting too close to criticality to being in the more, relevant operating point, which is subcritical. So during sleep deprivation or during wakefulness, You approach criticality and then norm pushes you down. I'm not sure about REM. It seems like a supercritical state. I don't know what REM does, but it makes sense that sleep is a homeostatic process altogether that is designed to get you back to a normal operating point, slightly below criticality. Yes?
Did someone try to measure this criticality in different animals?
Yeah.
And say this is has more cognition?
Not in this context, but criticality or measures of criticality, again, they belong to different families, have been shown in cultures, mice, rats, cats, monkeys, but I don't think it was analyzed mostly in resting state, not during task and not in correlation with task. So I don't think there's anything smart to say about proximity to criticality and intelligence along the evolution. Yeah. But I can say. Yeah.
What experiment will tell you you're wrong? Like how would you show it's not usually?
That's great. Show me an anesthetic that doesn't change the proximity to criticality. You give it to someone and they are anesthetized, they wake up from the surgery, they say nothing, everything was fine, but their brain, using multiple probes of criticality, remained close to criticality. These kind of things. Show me psychedelics that do not achieve the proximity to criticality. Show me conscious people that the, markers of criticality are too supercritical or too subcritical. So I want to be very bold. I don't think I'm right, but one last point, like in Einstein's theory of relativity, I know it sounds very strange now that I'm getting to that, he had an important principle, which is called the principle of equivalence, but he took it to a more extreme, which is called the strong principle. He said, not only that the inertial mass and gravitational mass are the same, but acceleration and gravity are the same. And only using that, he could predict that light would curve because of gravity. What we're saying here, I want to be really bold. I say that there is a mutual interaction between consciousness and criticality, that deviation from criticality would lead to loss of consciousness or proximity to criticality to higher consciousness. And the other way around, if you somehow change the consciousness of someone, I expect that his proximity to criticality or certain regions would also change. But it's a strong and bold prediction, and it can be refuted. David, what do you say? Okay. Thank you so much for the time.
כמה שנים אני הסתכלתי על משהו במראה כדי דבר אחר, סנסור. יכול להיות מעניין להסתכל על משהו נכון. מאמר על היררכיות.
You have more possible
לא לדוקטור יש לו...
Nobody's related, nobody's
He's the most diverse.
יכול לומר EEG לכל המספרה. לא, זה לא חושב, אני לא חושב שזה מספרה, נכון? זה צד של זה, זה בתוך...
זה לא ממש משנה לך אפילו מה גס. כן, אפילו לא צריך לעשות
אני יכול ללכת בבית, ולראות איפה זה מתפצל, אני מאמין שהפש, כאילו הדברים האלה יתנו משהו, למשל בפרוזר פגנוזיה, הם לא רק לא זה, או הבנים שופים עליהם, אני חושב שהם אולי יותר קריטים, אז אתה תוכל לראות את זה גם באופן דייק של יש מישהו שעבדתי, אני אביא את זה, בצון בבן גוריון, אני רואה יש לך סיבה שאני חייב לסמך לא, יש את זה בחורות קשרה לאיזה מישהו נראה לי שיש להם משפחה היא כאילו בצוף כזה שם מוקשרת אמרתי, אתה מסביר בכל הדברים את האנשים שיש להם איזה שם כלים מה קשה עזו להם כבר לא מעט בסוף הדברים יכולים להפרעות הקרה והקרה שאתה יודע תקשר אתה יודע, זה דבר של מציאות של EEG אין לי מערכת לתת להם לא, גם אם יש לה EEG בוא נתחיל לעצמם לא, כן,
וזה כאילו מצב?
אני טוען שאנחנו פחות קונשס למשהו דבר. יש לך כמה מזיקזיונים דבר. אני רוצה לומר שזה משהו כזה. כן. למשל, יש איתה, הרבה שזה דלתה שעושים להם, יש את זה לא תיאורטי. שהוא מדבר על בדיוק. כן, הוא הציע משהו לגבי הפרויקציה ולעצת את הסלקה ואיך אני שתגות עכשיו
קראתי לבהרבה
אנחנו לא מגישים את זה עדיין אנחנו מגישים את זה לא מגישים את זה בכל שצריכים לעבור של אני לא מגיש כי דווקא דברים כסיפור פיזיקה כן, יכול להיות שזה באמת על ידי טיפול שלך אני חושב שזה מאוד עניינים, אני חושב בבית שאמרתי עכשיו, נגיד מזגר שם. נגיד, אם עדיף על גבול דטר, הם אזורים שהם מאוד בעתיים, אחד אזורי שפה, עדיף על גבול דטר, קוראים להם קריטי, הם אחרי קוראים לטיפול, התמונה שלנו כל כך ספרה. ואז כאילו בסכיזופרניה, שוב, לא יודע להסביר, זה לא טוב המוכרת שלנו. זה מאוד הגיוני שבסכיזופרניה משהו משתבש שם, ואז אתה שומע הקולות בראש. כשמשהו משתבש, דווקא אני שומע את הקולות בראש. טיניטוס זה שיבוש כאילו יותר דברים בסיסיים. טוב, אחלה, כן. אני רוצה לעצמי להיות פרובוקטיבי. אולי אם חיים היה פה, הייתי יותר אדומה. חיים, ידעתי שחיים לא יהיה, אמרתי לו...
היית פחות פרובוקטיבי.
לא, אני אוהב להיות פרובוקטיבי עם חיים. כשהייתי איתו תלמיד דוקטורט, ואוהבים כבר רעיונות מעניינים אצלנו, עם חיים מאוד, זה טוב, אנחנו תיאורטיקנים, צריכים כאילו לבוא עם רעיונות, ונגיד לניסיונאים, רעיונות, דווקא הוא בעד, אבל הוא נהיה קצת יותר קשה. דיברתי איתו בגלל חלק מהדברים האלה.
לא יודע, אני חושב אותו נהיה דווקא יותר רע.
כן.
מתעסק בפרי וויל,
אבל כאילו, נראה שמבחינת הפילוסופיה, כאילו, קרא המון דברים, למד המון דברים, ונהיה קצת מתוסכל מזה, עכשיו הוא קצת מתוסכל.
תודה רבה.
ユダヤ人。少なくともナタリアマンは話してる。
どうですか、あれ。いつもの方が。みんななんか食べたと。ここなんか環境いいね。全然。
そうね。
キャンパスより。
キャンパスいいよね。
ここは新しい。トイレなんかすごいダイソンまでついてる。もうまあね、高級なところしか見えない。ダイソンもある。
ダイソン？
ダイソンは扇風機で、扇風というか乾燥機。
ああ、そうついてるの？
ついてるよ。トイレ。見てない？多分滝のトイレについてる。But it's not people probably was my imagination. I had to just start with the car. It does not have a seat. じゃあ終わったらとりあえず戻ってワルミさんとあれやるわ。発表の内容。発表内容やろう。
It's not very good.